Okay, the tape is rolling. For you guys online, I passed out just an activity, but I'm going to show you guys that activity. It's our recall activity that we're going to start with here in just a second about transformations. But before we do that, let me ask again if y'all have any questions about the transformations homework that's due tomorrow, right? Online people due tomorrow is our transformations homework. I think it's pretty, we went through some of that, several problems last time. So I think that's pretty straightforward. I know the topic was a little bit confusing when I presented it in the notes, but the homework I think is not that bad. But if you've got questions about it, here's your chance.
Just the last two, the stretching and stretching.
Yeah, shrinking and stretching are kind of the same thing, right? I think we did this one. Did we not do this one as well?
Yeah.
Oh, okay.
I picked it up in the home. Practice, but I didn't struggle.
Oh, well,
yeah.
But so maybe look at the, I don't know, maybe look back at the tape since we already did those. Remember, of course, this is going to be a horizontal stretch, right? Because you're multiplying x by a constant. If that constant were outside of the parentheses, that means you could move that product to the left-hand side, and then that would be a vertical stretch. Yes, so that's the part that's maybe a little bit confusing. It's kind of like adding or subtracting from x. It is counterintuitive, right? In the way that shifts the graph, correct? Well, multiplying by x is also maybe a little bit counterintuitive in its effect, because if you multiply by 2, for instance, that means you're stretching the graph by a factor of 1/2. So you're stretching the graph by 1/2. In other words, you're shrinking it.
I see.
Okay, yeah, right. And here, since you're multiplying x by 1/2, you're stretching the graph by a multiple of 1/1/2. But 1/1/2 is 2. So in effect, that is stretching graph by a factor of 2. Okay, so it's kind of, again, it's kind of opposite of what you might initially think. Okay, but if the, however, to make it even more confusing there, Amanda, if the coefficient were outside of the parentheses, okay, that means you could shift it to the left-hand side by multiplying or dividing, and that would mean y is what's being multiplied, right, by a constant. So that's going to give you a vertical shift or stretch. Okay, but again, the vertical shift or stretch is, you have to think about it carefully. So this is part that's really probably the only part that's maybe a little bit confusing. Let's look at, let me write it in up here. So if I have y equal 1/2 times f of x, for example, where the 1/2 is outside of c, right, not inside. That not 1/2 times y. You can think of it as 2 times y.
Yeah.
Because if you multiply both sides by 2, you would have 2y equals f of x, right? So that is going to stretch or shrink vertically. But it works the same. It's going to stretch it by a factor of 1/2, okay? Which is 1/2. So that means it shrinks it by 1/2. Shrinks it by 1/2. Well, you could have really just been left. You really didn't have to go. You wouldn't have to go through these manipulations. You could really see, oh, I have the 1/2 multiplied times the f of x. That means I'm going to shrink it by 1/2. Okay. So that one's kind of easy to understand its effect. It shrinks it by 1/2, exactly as you would expect. But if the 1/2 is inside the parentheses, it's opposite effect. Yeah. So if I have a 2 here, if I had y equals 2 times f of x, again, since you can shift that to the left-hand side by dividing both sides by 2, that's really something that's multiplied by y. All right, but what's its effect going to be? Just like this, it's going to stretch it vertically by 2. It's going to double it in size. Okay, so that's sort of how that works. Well, all right. So anybody online with a question on transformations? All right. So, well, I have an activity for you then. So we have a recall activity on transformation. So that's the sheet that I just passed out. So if you can, this one, yeah. There's actually front and back. All right, but let's start with the front. Okay, obviously. So I'm going to project this for the people online. If I can find my so there it is. Okay, so that's what the class is looking at on their sheet for you guys online. So you'll just have to sort of mimic this. It's easy to just do this in your notes as well on paper. So there's a graph of sine of x. That's what sine of x looks like. Okay, and so remember, you know, it's got lots of wiggles in it, right? Okay, and it repeats every. Remember, the graph of sine of x repeats itself every 2 pi units, right, along the x-axis. So sine of 0 is 0, and then sine increases right to 1, and then it decreases back to 0, and then it goes down to -1. That's at 3 pi over 2. Sine of 3 pi over 2 is -1, and then at 2 pi, which is a little bit more than 6, right? 2 times 3.14, a little bit more than 6, right there. Then sine goes back to 0, and then this whole pattern just repeats itself, right? Okay. So the sine curve just replicates itself, right, every 2 pi units. All right, well, that's not really crucial to know that to answer this question. What I want you to do is to just roughly sketch there a graph of this function. Okay, so that's a transformation of the sine curve, right? Okay, so can you graph that? What's that doing? And then graph this. All right, so what is that transformation of the sine curve doing? Okay, so we just kind of talked about this one, right? So that one you might be able to recall from what we just said. All right, and then this one's pretty easy also. What is sine of x plus 3? Keep in mind that keep in mind here now, see if I can turn this to drawing. Keep in mind that is that going to write for me? Keep in mind there that the 3 is not in parentheses. Okay, so the 3 there is not in the 3 there is not in parentheses. So if you had x plus 3 in parentheses, that would be something different, right? I don't know if what I was trying here is going to work. Wait a minute, you guys at home, all right, I'm just switching. There we go. Oh, all right, okay, I got it. All right, so can y'all do these quickly there? You don't want to spend, you know, some hard, right? So this 2 that you get, and you can cut that way. Okay, we just yeah, this is how it comes up. It's like there you go. 6. All right. You just scribble, oh, come on, remember. We're going to be talking a lot shortly here about transformations of sine function. Those are called sinusoidal functions. So these are examples both of sinusoidal functions, not quite the sine curve, right, but close, and based on the sine curve. And so that's why this recall practice is handy right at the moment. Okay, did y'all get something there? Sort of drawn in. Let's see if we can do this one. All right. So what effect is that? What effect is that transformation having on the graph of sine? Just verbally, what would you say? What? Yeah, it's just shifting that up by 3 units, right? So it's just going to take the whole graph and shift it up by 3 units. It's not shifting it to the left or the right, okay? Not shifting it to the left or right. If you want to shift it left or right, I'll show you how you can slightly change the formula, right, to shift it to the left or to the right, okay? But this is going to be just a vertical shift up. The reason is because the 3 there. The reason is because the 3 is not enclosed in parentheses with the x. That means that you can move that 3 if you wanted to the left-hand side with f of x. F of x is the same as y, right? So really this formula is similar to y minus 3 is equal to sine of x. And remember, when you add or subtract something from y, that means you are shifting it vertically, correct? Okay. And when you subtract from y, that means you're going to be shifting up. Just like when you subtract from x, that means you're going to be shifting to the right, correct? Okay. So so this is really just shifting up. So all you have to do is think if you can take that graph and shift it up by 3 units. So that means that 0, 0 here would go up to 3, right? The origin would move up to 3, and then the sine curve, right, goes up 1 and above the origin and goes down 1 below the origin, correct? So when you're graphing this, you would graph it up to 4, right? Okay, and then down to 2, 1 above 3 and 1 below 3. All right, let's see if we can kind of plot this now. So it's going to go up to 4, right? Down to 2, right? And then back up to 3 again, a little bit more than 6. So there's a really ugly graph of that, okay? And of course it keeps going on the, left and the right, correct? So I'm going to shift up something like this. So y'all's graph is probably better than, looks better than mine, okay? Now, if you want to shift to the left or the right, put the x in, put the 3 in parentheses with the x, okay? That means you cannot shift the 3 to the left-hand side in that case. It's trapped with the x inside parentheses, okay? So that is a transformation along the x-axis. That means you're shifting left or right. In this case, which way would you be shifting? Since you're adding 3, left, right, okay? Since you're adding 3, that means you're shifting. Yeah, yeah, you're shifting to the left, okay? So we would just take this whole graph up and and move it over to the left by okay. All right, so what about a 3 sine of x? So what effect does that have? That's a vertical stretch, right? Okay, so in effect, you're just stretching that graph by a factor of what? 3, right? Okay, so instead of it going up to 1 on the y-axis, right? This curve is going to go up to 3 on the y-axis, right? But it's not going to get shifted, so the intercepts are going to stay in the same position, but it's going to go up to 3 and down to -3 like this, right? So probably not going to draw this very good on the other side, but something like that, right? Okay, so you've just changed the height of the graph, right? If you wanted to shrink it or stretch it horizontally, right, where would the 3 go? Right, next to the x, right? So if you wrote y equals sine of 3x, that would stretch or shrink the graph horizontally. In fact, how would that change the graph? It's going to stretch it horizontally by a factor of what, though? It's not going to be 3. 1/3, right? Okay, a factor of 1/3. So that is in effect shrinking the graph. Okay, so this transformation would shrink the graph. Stretch it by a factor of 1/3 means you're really shrinking it. So notice that this graph would oscillate a lot more rapidly. Okay, this graph would oscillate a lot more rapidly because of the fact that it's been shrunk, right? So it would have more oscillations than the original sine does. Again, why is that a factor of 1/3? When I put the 3 here, why did this stretch it by 3 and this stretch by a factor of 1/3? Because that 3, remember, is really an effect on y. So if you move the 3 to the left-hand side, you would have what? Y divided by 3, divide everything by 3, right, is equal to sine of x. So that's 1/3 of y, which means you're stretching by a factor of 1/1/3, which is 3. Okay, all right. So that's why this the 3 here really makes the graph taller, but this 3 is going to shrink the graph. It's going to shrink the graph instead. All right. Well, let's try what's on the back page here. If I can scroll down. So fortunately here, you don't have to draw any graphs. All right. So what we have here on the left-hand side is a graph of x cubed minus 3x squared. Okay. So x cubed minus 3x squared. And on the right-hand side, we have a graph of another function called g. All right, and that's just, you can tell that's just a transformation of f, correct? Because the shapes of the graphs are the same. Okay, so g is just a transformation of f. So how would we transform formula for f, right? What transformations would we apply in the formula of g? So I'm giving you some suggestions of what you're going to do. Looks like we're not going to multiply f or x by any, right? Looks like we're just making shifts, correct? Okay. So what shifts could you make to take f, right, and make it okay? So the shape of the curve is exactly the same. It's just been translated to a different location. So what translations here, what shifts did you apply? And then the second box, we go ahead and fill those translations into the. Okay. All right, so you see what you're doing there. All right, so see if you can just count there and see what those shifts are going to be. Then don't press.
Oh. That's why.
Is it we're on this side?
Oh, that's how.
Yes. Yeah, go in the box. So what you're gonna do is just take what is. No part. Just.
Okay.
That's it. Right. Here. And so, that's right. So, okay, you're replacing X plus X with X plus. Now try to wrap that. That is correct. Now, what is that? So, it's X plus. But don't try to multiply that. Yeah, you're gonna end up with a big messy expression. Don't try to see. A lot of algebra. So you don't need the. Pretty like that. Oh. So that's good. That's a shift. So. That's so okay, I'm gonna pass the roll sheet out while we're talking about this one. Okay, let's get someone in line to help us with this. Okay, so we got lots of participants online today, so that's good. So can y'all tell us, in moving from here, from this graph to this graph, right, what transformations, what shifts have we used there? All right, so so clearly we've had a it looks like this has been shifted up, right? Okay, because if you focus, there's any number of points you can focus on, but say if you focus at this point at the origin, right, that peak point looks like in G, it's right there, correct? So that's clearly up, right? So how far up have we shifted that point? Someone online, how far up have we shifted that point? Four. Yeah, Giselle, perfect, right? Okay, so Giselle, in the formula, where will we put the 4? So, right, because I've obviously got a shift of 4. Where does it go here in our formula? Yeah, plus 4, right there. I'm going to assume you mean right there. Yeah, that's right. The last one. Yeah, correct, Giselle. You got that right. Okay. Now, so again, the question is, why is that plus instead of minus? Because this 4, because it's outside of parentheses, you could move it to the left-hand side. So you would have g of x, which is the same as y, right? Minus 4 equals f of x plus whatever that we fill in there, correct? And so see there, you're subtracting 4 from y. And when you subtract from y, that means you're shifting up. Just like when you subtract from x, you're shifting to the right-hand side. Now, well, let's see what goes in this slot, right? Okay, because there's also been a horizontal shift. It looks like this point, again, if we key in on this point, it looks like we moved it from the origin on the x-axis over to where on the x-axis? That looks like what? What does that look like there? -3, right? Okay. So Jacayla says, oh, in this point, in this spot, I want what? 3, right, Jacayla? Okay. So I want to put that I want to put that 3, right, Jacayla, there, because that would correspond to a horizontal shift. And since that's +3, that means we're shifting to the left. Okay, but that's exactly the way we want to shift. Oh, so there's the formula. It's f of x plus 3 plus 4. Now, what is f of x plus 3? We have the formula for f, so we can fill that in. F of x plus 3 would be x plus 3 cubed. So substitute x plus 3 for x, right? Minus 3 times x plus 3 squared. And then don't forget the 4 that you put on at the end. So there's the complete formula for the function g. We don't have to cube x plus 3 or square x plus 3. That would be a lot of algebra. We could do that, but that would take us a little while, so that's not necessary. Okay, here's the formula for the function g. Okay, see, just that easy. All right, so now I keep promising you, right, that we're going to come back to transformations because we're going to apply those to sine curves and cosine curves and other trig functions as well, but in particular sine and cosine, to create again what are called sinusoidal functions. But we're not quite ready for that. All right, we have one more topic in functions that we want to go through first. Okay, and this is another way I mentioned last time of taking an existing function, in this case just a single existing function, not two existing functions, but taking a single existing function and creating a new function from it. Okay, and this idea is called creating the inverse of a function. So suppose you have a function, right? So it's just some old function, and then its inverse function would you denote by putting f with a superscript of -1. But this is not an exponent. Okay, this is not an exponent. This is just a naming mechanism. So this is just a superscript of -1. And the way you read this is exactly what I said. This is you read this as f inverse. So don't say f to the -1, because if you say f to the -1, you're treating the -1 as an exponent. But the -1 is not an exponent. It's just a naming tool. Okay, to create a name for this new function I'm creating, which is also called the inverse function. All right, so you read this as f inverse. Now, here's the way the function f inverse works. Okay, it's a little bit the definition here looks a little bit confusing, but when I explain it, it's the idea is quite easy. All right, f inverse of b. So if you give b as input to f inverse, you're going to get the result, the output a, if and only if for the original function f of a was equal to b. What does that mean? All right, so here's what that means. For the inverse function, what it does is it takes the original function and it flips the inputs and the outputs. It reverses the inputs and the outputs. So if in the original function, you had an input of A and an output of B, okay, so an X value of A and a Y value of B that match that, then that means in the inverse function, if you have an X value of B, your Y value is going to be A. See, you're switching the input and the output. You're switching the X and the Y, so to speak, okay? That's how this new function, F inverse, is going to work. So it's just the original function with the X and Y's flipped. Let's take a very simple example of this, okay? With where I have the function written down, not as a graph or as a formula, but it's just a set of ordered pairs. Remember, a function is a relation, and a relation is a set of ordered pairs, right? But once we define function, we usually don't talk about functions as sets of ordered pairs for very long. But here I went back to the original definition just to illustrate this idea. Okay, so here's a function f, right? So there's its set of ordered pairs, and I have another function called g, and there's its set of ordered pairs. All right. So let's write down now, if we can, let's write down the inverse function for f and the inverse function also for g. Okay. So what is f inverse going to look like? So it's also going to be a set of ordered pairs. All right. But how do we create the ordered pairs for the function f inverse? You just reverse the coordinates, the x's and the y's in each of the ordered pairs for the original function f. So if 0, 2 is part of f, that means for f inverse, you're going to have 2 zeros. See, just flip the x and the y's. Or since 1, 4 is in f, that means 4, 1 is going to be in f inverse. See, it's just that easy. Let's see what else would be there. 2, 3, we would flip that to 3, 2. And then 5, 3, we would 3, 5, we would flip that to 5, 3. So there's your inverse function. Just that simple. Let's check and make sure that is a function. This is the problem with inverses. Okay. Sometimes when you try to create the inverse of a function, you will end up with a creature that's not a function. All right. You'll end up with a relation that's not a function. That's what you have to be careful of. Let's see, is f inverse really a function here? Remember, in a function, you cannot repeat what? You cannot repeat x's. So do we repeat any x's here? There's 2, 4, 3. What's this one? 5. Yeah, so no x's are repeated. All right. So there it is. There's the function. There's the function f inverse. So notice that works exactly the same as this description, because see, in the original function f, right? In the original function f, if I can get my pen to work again, there it goes. In the original function, I think, in the original function f of 0 was equal to 2, correct? Because the ordered pair 0, 2 was part of that function. So, but in the inverse function, f inverse of 2 is equal to, f inverse of 2 is equal to 0. I keep touching my. Shoot, well, let me just draw it with the mouse here for a second. So f inverse of 2 is equal to 0. Okay, right? So the x's and the y's there, have just been flipped. There we go. Now let's see what happens with G. I included that example for some reason. So maybe when we try to compute G inverse, we'll come up with something that's not a function, right? Let's try writing down G inverse. So what does it look like? G inverse looks like? Well, when you flip the ordered pairs, what do you get? 1 and 0 and 0 and 1. And then what else there? 3 and 2. And then what's the last one there? And see, there's a problem, right? Because when you flip that last one, notice what happens in G inverse, you end up duplicating X, right? And you cannot have that in a function. So that means that the original function G does not have an inverse function. So that's a problem with inverses. Not all functions have inverses, okay? Some of them do, but some of them do not. And so you have to be careful of that. You can't just create the inverse of any function that you like. A function that does have an inverse is called a one-to-one function. So if a function has an inverse, it's called a one-to-one function, also called an invertible function. So how do we recognize when a function has an inverse? Well, that's not always easy to do, okay? But the basic idea is you cannot repeat the y coordinate, right? Okay. If you repeat the y coordinate in a function, remember, you can never repeat x coordinate function, right? But if you repeat the y coordinate in a function and then you flip x's and y's, what's going to happen in the inverse function? You'll have a repeated x, right? So that function, the original function, would not have an inverse. So to have for a function to have an inverse, for a function to be a one-to-one function, cannot repeat the same output value. Okay, you can never repeat x, but for a one-to-one function, you cannot repeat y either. All right. So that's the basic test of if a function has an inverse or not. Okay, that's what this sentence essentially says. Okay, you cannot repeat y values, okay, if a function is going to have an inverse. All right, so let's look at a function here and let's see if we can figure out if it's a one-to-one function. So this is a function that you would, the way you'd more likely see a function given to you, not as a set of ordered pairs, but here as a formula. So let's see if we can decide if this is a one-to-one function. And if it is, let's see if we can write down the formula for f inverse, okay? So there's the formula for f. Let's see if we can figure out what the formula for f inverse is going to look like. Okay, the way I'm going to do this is by using a graph, okay? So a graph is really helpful as a tool for you to help you understand if a function has an inverse or not. And so I'm going to make a graph of that function, that original function, 3x minus 4. But that's an easy one to graph, so I don't have to, I can do this by hand. Because what sort of curve is 3x minus 4? That's what? That's a straight line, right? Yeah, that's going to be a straight line. So that's a straight line, and the y-intercept is what? Minus 4. So when x is 0, y is minus 4, right? And all we need is another point on the line, right? And then we can draw the graph. Let's plug in, let's try x is 2. And if x is 2, what's y there? 2 also? I'm just plugging 2 in for x here. So I get 6 minus 4 is 2, right? Let's try 4 here. Oh, maybe that's too big. Let's try 3. What would that give us? 5. 3 times 3 minus 4 is 5. All right, so there's 3 points. That's more than enough to draw the graph, right? Because the graph is just going to be a straight line. So let's draw the straight line. Don't pay attention initially here to this dash line that I have drawn in here. That's not part of the graph, but I've drawn that in for a reason, okay? Because that's going to be helpful to us a little bit later on in studying inverses. All right, so let's draw the graph of f. So 0 and minus 4, 1, 2, 3, 4. So it goes through this point, right? And then 2 and 2. So it goes through this point. By the way, that dash line is a 45-degree line. Okay, so the x and y coordinates are supposed to be the same. That's why the 0.22 falls on that dash line. And then also what, 3 and 5? So 3 and 5, did I do this right? 3 and 5, right there. Okay, yeah, those look like this fall in a straight line, right? So maybe I did this right. I can connect them with a halfway decent straight line here. All right, so well, I almost got it. I curved it a little bit at the top. Let's take that curve out. Top there. That looks a little bit better. All right, so there's the graph of the original function f. All right, now let's see if we can make a graph of f inverse. Okay, now I don't really know much about f inverse at this point, right? Okay, I have no idea really what the graph is supposed to look like, or certainly not yet what the formula looks like, but I do know a little bit because I know these ordered pairs 0, -4, 2, 2, and 3, 5. I know they're on the graph of f. So I know some ordered pairs that are on the graph of f inverse. What ordered pairs do I know are on the graph of f inverse? How does f inverse work? F swapped. So you can just swap these coordinates, you see. So you know on f inverse, when x is -4, y is going to be 0. Okay. Or when x is 2, oops, y also is going to be 2. See, flip these. Or when x is 5, what's y going to be? 3, right? Okay. So let's plot those points and see what they look like. So I have -4, 0. Did I get that in the right spot? Yep. Okay. And what else here? 2 and 2. So that point also. And then what? 5 and 3. See, 1, 2, 3, 4, 5, 1, 2, 3, right there. And now that's just too much to be a coincidence, because all of those points also happen to what? They all fall in a straight line. Okay. So I'm thinking, all right, that the graph of f inverse is a straight line. Okay. And we're going to find out soon enough that that is correct. So here's what the graph of f inverse looks like. It's really just a straight line. Okay. Also, okay. Well, so that's sort of comforting for this straight line. Its inverse existed, and all apparently exists at least, and turns out to also be a straight line, which means that I can write down its formula, because I know how to write down formulas for lines, right? Okay, you remember that from test 1? All right, well, we'll write down the formula here in just a second. So this is what f inverse is going to look like. Before we graphed f inverse, when I'm just looking at the graph of f, can y'all tell from the graph of f that it's going to have an inverse? Can you tell that from the graph? Because again, how do you know when a function has an inverse? There's no repeating what? No, that's function. Y value. Look at this graph of f. Are you going to get any repeating y values here? No, you're not going to get any repeating y values. For f to have a repeating y value, what would have to happen there? And for f to have a repeating y value, what would have to happen in the curve or get a repeating y value? What now? A vertical line. Yeah, a vertical line would have repeating y value. So a vertical line is bad. Okay, what else, Jad, would give you a repeating y? A circle. Yeah, okay. A circle is going to have repeating y values. In fact, if you had any sort of curve, right? Not curve, but a curve like this, correct? That would give you a repeating y value, right? Okay. So if you have a turning points, right? Like this, okay? You're not going to have an inverse, right? Because that will give you a repeating a y value, okay? Circles are like that for sure, right? Okay. Have lots of turning points in them. So circles do not have inverses, but circles are not functions to begin with. Okay? So so the question for circles is kind of moot, right? Because a circle is not a function to start with. We only talk about inverses of functions usually. All right, well, let's try this again then. Okay, so now this one's harder though. So we want to show that this function x cubed minus 2x squared minus 3x is not 1-to-1. So in other words, I do not want it to have an inverse, okay? I don't want it to have an inverse. So the convenient way to discover this is to look at the graph, okay? Because the graph will give you a strong clue as to whether this has an inverse or not. Now, this is not so easy to graph though. So I would suggest here that you make a graph with or a calculator, all right? So I'm going to use Desmos to make a graph of x cubed minus 2x squared minus 3x, right? This is definitely not a straight line. So this is not one that's going to be easy to graph by hand. So let's have the computer draw a graph for us of this one. Let me see if I can find it. I think it's this example. So yeah, there it is. Okay, is that it? Yeah, x cubed minus 2x squared minus 3x. So there's the graph. Well, that one has some turning points, right? Okay, so that one's got a couple of turning points, right? It's got a local maximum right there, and it's got a local minimum right there. So I'm thinking doesn't have an inverse because it's going to have some repeating y values. What's a y value that repeats, in fact? -6, right, Emil? You're right, okay? This point has y coordinate -6, right? See, there's -6, so it corresponds to this horizontal line, right? So that point has, on the curve, right, has a y coordinate -6. That point has y coordinate -6. Actually, that's pointing at that point, and not quite pointing at the right point, right? That's the turning point. But that point also has a y coordinate -6, and this point has y coordinate -6. So 3 points there, right, have the same y coordinate, so not going to have an inverse. Because think about it graphically, Jad. Let's think about it graphically. If you flip these 3 points that Emil was showing us, the 3 points that have y coordinate -6, right? If you flip those points, then you're going to get 3 points in the inverse graph with x coordinate what? What? See, these 3 points have y coordinate -6, right? So if you invert those points in the inverse graph, you would have 3 points with what? X coordinate -6, right? So you would have 3 points along this vertical line, okay, which you cannot have in a function. Someone else said 0, right? These intercepts, right? They all have y coordinate 0. Those points we can see exactly, right? So there's 3 points with y coordinate 0, and so you can't have that, right? Okay, in a 1-to-1 function, you cannot have that. So so definitely this function f is not 1-to-1. Let me give you just a real easy, and you may be aware of this test. So if you want to know if a function is invertible or not, okay, if it's 1-to-1, when you draw the graph of the function, and if there's any horizontal line that will cross the graph more than once, not going to have an inverse, right? Any horizontal line that crosses the graph more than once means don't have an inverse. The x-axis is an example of that, right? Okay, the x-axis is a horizontal line, and that crosses this curve 3 times. So this curve cannot have. So it's a perfectly good function. It's just not a 1-to-1 function. Yeah, Jed. When x has what? No. Not. Yeah. Not always true. Yeah. Yeah. Yeah, there are plenty of examples where you will have formulas where x has a power higher than 1 and have an inverse. Okay, but not this one. All right. All right. Now I'm going to show you this property of inverses. And at first it looks just like it's kind of a curiosity, but it actually turns out to be really one reason why inverses are really the main reason why inverses are of interest to us. Okay, so this is called the inverse function property. So suppose that you have a function f, okay, and it has an inverse. All right, its inverse is an, for some reason here in this statement of this property, we gave a name to this inverse function g. Okay, but f inverse is the name of a function, so you really didn't have to pick up a separate name for the inverse function. All right, but here we called it the inverse function g. Then what this property says is that if you compose, notice we're using composition here, if you compose a function with its inverse, so take a function and compose it with its inverse in either order, the inverse simplifies to just x. I'm sorry, the composition simplifies to just x. So if you compose a function with its inverse, the formula for that composition simplifies to just x, not a constant, but just the variable x itself. So again, we're not going to prove that, but again, at first that looks like, okay, well, that's an interesting fact, or that's a fun fact, but cares. But that turns out to really be why inverses are, this property really turns out to be why inverses are mostly the reason why inverses are useful to us in practice. All right, so let's apply this just for fun here, and to these two functions. So suppose we have a function named f, and formula is 2x plus 3 over x minus 1. And then we have another function g, and its formula is x plus 3 over x minus 2. And at first, we don't know really anything about the relationship of those two functions. But we want to show that these two functions, f and g, are really inverses of one another. So really, f and g are really inverse functions. So g of x is really the same as f inverse. Or you could also write that f of x is the same as g inverse. In other words, what I just said, these functions are inverses. So how do we test that? And the way you determine that is by using composition. So if you compose the two functions and they really are inverses of one another, that composition will simplify to just plain x. If it simplifies to something other than x, they're not inverses of one. Okay, so there may be some other relationship between the function, but they're not inverses. But if the composition simplifies to x, then no, they're inverses. Technically, you should check that in either order, but usually in one order will do. Okay, there are just very special examples where you can compose in one order and get x, and then you compose in the other order and don't. Okay, but those are very rare. So we really need to only check here in one order. So let's do g compose f, but we could do f compose g if we wanted to. All right, so let's remember composition. Just learned about that last time, but y'all done composition before. So how does composition work? Remember, g compose f of x will be g of what? F of x, right? That's what I kept repeating last time. G compose f of x means g of f of x. You're going to use f of x as input to the function g. That's going to get a little bit messy here. So let's see what that ends up looking like. Well, the first step is not too bad because you know what f of x is, right? Because you have a formula for that. So where you have f of x, just plug in f of x. So that's 2x plus 3 over what? X minus 1. So that's easy enough. Yeah, it's the second step that's hard. Okay, because now we have to compute g of 2x plus 3 over x minus 1. That looks terrible, right? Because I have to take all of this and plug it in for x in the formula for g. So that's going to get messy. But let's do it. So let's not get shy. Because, Iris, what's supposed to happen at the end? This is all supposed to simplify to what? If these really are inverses of one another, what does this composition simplify to? Just what? X, right? Just plain x. So maybe things aren't as bad as they look. all right? But let's see. So I take 2x plus 3 over x minus 1, and I'm going to plug all of that in for x in the formula for g. So I get 2x plus 3 over x minus 1. Plug that in for x. So don't forget this plus 3, right? Over, and now I have to take this, all of this, and plug it in for x in the bottom. So I have 2x plus 3 over x minus 1. And then don't forget this minus 2. Okay, that looks intimidating. What is that thing called now again? We mentioned this last time. When you have a fraction inside of a fraction, smaller fraction inside of a bigger fraction, such a thing is called what? What? Yeah, this is a complex fraction. All right, so we're dealing here with a complex fraction, which we want to try to simplify. Okay, so this is not the easiest thing in algebra to do, simplifying complex fractions. All right, because it really does test a bunch of skills from algebra. That's why it's kind of tricky. All right, so let me show you what the idea is, though. All right, it's the same thing we did last time, if you recall. Here's what I'm going to do. I'm going to combine the two terms in the numerator into one fraction. In other words, I'm going to add together 2x plus 3 over x minus 1 plus the 3. And I'm going to get one fraction in the top. And I'm going to do the same thing in the bottom. In other words, I'm going to subtract the 2 from the 2x plus 3 over x minus 1. Now, you can think of 3 as being 3 over 1. So you can think of this as adding two fractions together in the top. We'll do the same thing in the bottom. You can think of the 2 as being 2 over 1. But let's work it on the top first, one step at a time here. So I've got these two fractions to add together in the numerator. Well, unfortunately, I cannot just combine those fractions because I don't have a common what? Denominator. I need a common denominator, okay, before I can add the fractions together. What can I use as a common denominator? X minus 1, right. Remember, if you need a quick common denominator, it may not be the best one, but if you need a quick common denominator when you're adding two fractions together, you can always just multiply the two denominators of the fractions you're adding together. That will give you a common denominator. But this would be x minus 1 times 1, which is just x minus 1. Ooh, that works out nicely. Okay, so I'm going to combine these two fractions with a common denominator of x minus 1. Now, this fraction already has x minus 1 as its denominator, so I'm really looking good there. I don't have to do anything to that first fraction. But the second fraction, I'm going to have to change it, right? Because I need it to have a common denominator of, I need to have a denominator of x minus 1. So to get that denominator of x minus 1, you just cheat here, you know? You just multiply the x minus 1 into the bottom. But, you know, you can't change the value of the fraction. So you also have to multiply the top by what? Yeah, you have to multiply top and bottom by x minus 1. Okay. X minus 1 over x minus 1 is really 1. And so you're not changing the 3, but you're going to make it. In fact, what's it going to end up looking like? You'll have 2x plus 3 over x minus 1 plus what? 3 times x minus 1? Because you got to multiply the tops together, right? Over 1 times x minus 1, which is just x minus 1. Now you can add them together and you'll get something over x minus 1. All right. Y'all tell me what I get now. All right. So when I add these two numerators together, go ahead and combine like terms. So you have 2x plus 3 times x minus 1. Go ahead and combine like terms for me and see what you get. So what does the top turn out to be? Still going to be kind of messy. The only advantage is it's one fraction. We're going to end up with one fraction in the top. Notice I haven't even done the bottom yet, but we're going to come back and do that. All right. So what do I end up with? So what's 2x plus 3x minus 1? Well, that's pretty easy. What does that end up? What? 5x. I already got perfect. It's just 5x. Oh, nice, right? Because ultimately, when you take 3 times x minus 1, you get 3 times minus 1, which is minus 3, right? That adds to that 3 to give you 0. So you just end up with the x's, which is 2x plus 3x. Great. So that's not so bad. 5x over x minus 1. Now I have to do the same thing in the bottom. So what did I do there? Let's see. Ooh, I'm not leaving myself much room, right? So let me move this down a little bit. That down a little bit. I lost the top of my thumb. That back. Okay, so same idea in the bottom, right? So I've got to have a common denominator to add these two fractions together. Obviously, that common denominator is going to be x minus 1 again, right? So I need to change the 2 over 1. So its denominator is x minus 1. So I'll multiply top and bottom by x minus 1. So what do I end up with there? It looks like 2x plus 3. And then minus 2 times x minus 1, right? Minus 2 times x minus 1. And now my denominator is going to be x minus 1, my common denominator. So I can combine those two fractions together. So I get something that looks like this, right? 2x plus 3 minus 2x minus 1 over x minus 1. What does that simplify to? Is it 4x plus 1? You have 2x here. How many x's are you going to get there? You multiply 2 times x minus 1. How many x's is that? Minus 2, right? So don't I have, well, let's write it down. We have room, so let's write it down. So I have 2x plus 3 minus 2x plus 2, right? Over x minus 1. And so works out nicely, right? What do you get? The x's drop out. And you just get 3 plus 2, which is 5. There you go. So you have 5 over in the bottom here, x minus 1. Still a complex fraction, right? Because I have these two smaller fractions inside of this big fraction. Now, what did I achieve then by adding the terms in the top and adding the terms in the bottom? What I achieved is now I'm going to treat this as a division problem. This big fraction, I'm going to treat it as a division problem. We're taking this fraction and dividing it by fraction in the bottom. So let's write that down. As a division problem, I have 5x over x minus 1 divided by 5 over x minus 1. So I'm going to write it down different. Instead of as a fraction, as I mentioned, let's write it as a division problem. Same thing. And the reason I want to write it as a division problem is I can remember, how do you divide one fraction by another? So what's the rule from grade school for dividing one fraction by another? That's right, you take the reciprocal and multiply, right? Okay, so that you learned in 5th grade, maybe. So I know you all got past 5th grade, right? Okay, so your 5th grade teacher, I don't remember. God, I've forgotten. Sad. I think about it. Now, what happens here, though, in this multiplication? The x minus 1s cancel, right? And the 5s cancel, and look what we end up with there. Yeah, just plain that, right? Ah, last, okay. That's what we wanted. All right, so what's the moral of that story? Now they are inverses, yeah, right. Yes, because the composition turned out to be what? Just x, right? So when you compose functions and you just get x, they're inverses of 1, right? So again, that curiosity, what appears to be curiosity, is really a useful property of inverses. That's really what makes inverses powerful for us. Actually, now let's try this again. I'm going to come back to I'm going to come back here to the graphs, but let's we're going to try this again, except now we're going to find the formula for the inverse function. So in that previous example, you had two formulas and you were just composing them, right? And just trying to discover if they were inverses. But here I'm giving you a function named g, which is 3x minus 4 over x plus 1. That's not one of our previous examples, was it? That wasn't the previous example, was it? This is slightly different, right? So 3x minus 4 over x plus 1. And first, we're going to check and see if it's a one-to-one function. So we're going to see if this function has an inverse. We'll do that by looking at the graph. Okay, so we'll try to figure that out by looking at the graph of 3x minus 4 over x plus 1. And then we want to see if we can discover the formula for G inverse. So we're not going to have the formula given to us. We're going to just see if we can figure it out. Okay. All right. So first, let's look at a graph of 3x minus 4 over x plus 1. So let me see if I've got that one graphed already. So remember now, if you're doing your homework on composition and inverses, remember you have a link to this Desmos tool, right? So if you're asked to make a graph of a function, you can do that quickly. There's the graph of, you can't see all of it very well, right? If I move these things around, there you go. Okay, so there's the graph of 3x minus 4 over x plus 1. So it's kind of a funny graph there. Notice there's a break in the graph right here. There's a break in the graph right there. What value is that on the x-axis? Where there's a break there. Graph is not connected. Is it -2? It looks like it might be -2, but it's really not -2. You can see it from the formula. It's -1, right? There's a break at -1, okay? Why? Because what number is not in the domain there of that function? Yeah, -1 is not in the domain, right? Okay, because -1 for x would make this denominator 0. So -1 not in the domain. So really there's a break right here at -1. It looks like it's at -2, but it's really at -1. Right. So this graph has two branches to it, but the fact that it's two branches is kind of meaningless to us, because what we really want to see is, are any y values going to be repeated, right? Okay, so do we have any repeated y values? I don't think so, right? Okay, if you look at this branch, right, always just going up, right? Look at this branch, also just going up. Now, the question you may have is, is there any place on the far left, I'm sorry, on the far right or on the far left, where this branch gets high enough to sort of repeat a y value that was on this branch? Okay, that's hard to tell here, but the answer really is no. Okay, so there aren't going to be any repeat y values here. Okay. All right, so let's then dive into seeing if we can figure out what is the formula then for the inverse. Here's where our logic really just is so beneficial to us. Okay, let's write this. Let's write this formula instead of g of x equal 3x minus 4. Let's for the g of x, let's change that to y just temporarily. So let's write this as y equal 3x minus 4 over x plus 1. Now, what happens with inverses again? What's the whole scheme for creating an inverse? What do you flip? Yeah, you flip the x and the y coordinate. So that's what we're going to do in this formula. We're going to flip x and y. Okay, so I'm going to interchange here x and y. That really is the formula for the inverse function, okay? That's it. But now normally you wouldn't write a formula for a function is x equal to, you would instead write it how? Yeah, y equal. So let's take this and solve it for y. So I'm going to take this equation and solve it for variable y. Okay, so I want to write it as y equal instead of something instead of x equals. All right. Well, let's do this. So here's what I'm going to do. Let's multiply both sides by y plus 1. That's to get the fraction. All right. So, of course, the y plus 1's divide out. That's the whole point of multiplying both sides by y plus 1. So, and now let's multiply the x into the y plus 1. So you get xy plus x, correct? Right? Now, remember, I'm trying to solve this for the variable y. I want y equals something. So let's gather our y terms. Let's get our y terms on one side of the equation, the terms that have y on one side of the equation, and let's get the terms that don't have y on the other side of the equation. So it doesn't matter which side you choose, but I'm going to move the y terms to the left-hand side because that's ultimately where I want to have y, right? It's on the left-hand side. So let's take this 3y and move it to the left, along with this xy, because this xy has a y in it as well. Now, this x term doesn't have y, so I'm going to pull it back to the right-hand side. So let's see, what do I get here? X times y minus, don't forget to change signs there, 3y is equal to, what is this, minus x minus 4? Now, from these two terms, since they both have y in them, I'm going to factor out the y. So I have y times x minus 3. See, I know I can factor because I moved all the y terms to the left-hand side. So all those terms have y in them, so I know I can factor that out. So I get y times x minus 3 is equal to minus x minus 4. Now, how can you finish solving for y? So easy at this point. By what? Sure, right, Amanda. So we just get y is equal to what? Minus x minus 4 over what? X minus 3. There it is. There's the formula for the inverse function. That's what we were looking for. Minus x minus 4 over x minus 3. Wow. It's really easy. If I gave you these two formulas and said, check to see if those are inverses, what would you do? You'd have to compose them and come up with what? X. It's really easier if I just gave you this one and said, find the inverse and check to see if it matches that, right? Okay, that's really less work than doing the composition. All right, well, I'm gonna let y'all try one then really fast here. Okay, so there's a function named f, 2 over x plus 5, and we want to see if we can find its inverses. Actually, we're going to do that really not even being sure that f has an inverse, because I'm not going to look at the graph of 2 over x plus 5. I'm just going to, let's just haul off and do it. So see if you can find the formula for f inverse. By the way, if when you're trying to find the formula, if you run into a problem, then you'll know that the original function doesn't have an inverse. Okay, so there's another way of telling to see if the function has an inverse. So what's the first step here? First write it as this, right? Y over 2x plus 5. And then the key step is what? Yeah, reverse the x and the y, right? Because that's how inverses work, right? You just flip x and y, okay? So see if you can do that and then solve for, see if you can solve for the variable y resulting equation. So that requires a little bit of algebraic skill. It's not too bad though. All right, so you guys at home also, right, we're just seeing if we can find this formula So after you flip the X and the Y guys at home, can you then solve that for Y? So then you'll have something about that. But
Oh, I was like, what is that?
I think that's, but I was like, X, Y, Y. Yeah. You have to multiply Y by every. Multiply it here again. Multiply it. Multiply every. Actually. I think that's it. Yeah.
How was the neighbor?
I'm get rid of the Y. Every. 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 Interchange. Every. So first you get change, right? And wherever you have X, put X. That's T first X. But first, every. Every. Okay. All right, let's write quickly down. So some of you got a little bit jumbled there on the algebra of solving the equation. Okay, but so let's clear that up. So first, interchange X and Y, right? So that's how inverses work. They interchange X and Y. Okay, and so most people were able to get that down. And this really is the formula for the inverse function. It's just not written in a form that you want it written in, right? We want it written in the form y equals. So I have to solve this equation for y. So to do that, the easiest first step, I think, is to get rid of that fraction 2 over y. All right. So to do that, you would multiply by y, this fraction by y. So the y's would divide out. But when you do that, when you multiply this fraction by y, to keep the equation balanced, you have to multiply everything in the equation by y. So you have to multiply this by y and this also by y. So that gives you x times y, multiply this by y, equals 2 over y times y. The point of that, remember, is so we can divide out the y's. And then plus, you also have to multiply 5 times y. So you get xy equals 2 plus 5y. So the only really progress we've made there is we just got rid of the fraction, right? But usually equations without fractions in them are a lot friendlier to work with. Now, still have to keep solving though. So what's the next important step here? Since we're solving for y, what do we do? That's right, you move the 5y to the left, right? Because you want the y terms together on one side of the equation. So take the positive 5y and move it to the left. So that would give you xy minus 5y. Don't forget to change the sign, equals 2. Here's the step now where students always forget, okay? Factor out now the y. You have y in both of these terms, so you can factor that out. So you have y times x minus 5 is equal to 2, and now it becomes easy to solve for y. Just divide both sides by x minus 5, right? So don't, after the factoring, then it's easy to solve. So you get, there it is, 2 over x minus 5. So there's the formula for the inverse function. Looks, in this case, quite a bit different, right? The original function, 2 over x plus 5. There's the inverse function, 2 over x minus 5. So this function does have an inverse, okay? Does have an inverse, all right? Because there we found it, the formula for the inverse function. All right, let's take a break there, and then we'll come back. And the last thing we want to say about inverses, we know how to find formulas for inverses, but we want to know, what do graphs of inverse functions look like? Because it turns out we can know that also initially if we know the graph of the original function. There's a close relationship between the graph of the inverse and the graph of the original function. And we're going to show you what that is, okay, when we get back. All right, so let's stop here. I'm going to pause this. Okay, so I'm going to show you here what I mentioned before the break. So, and that is that inverses and the functions and their graphs and the graphs of their inverses have a really strong geometric relationship that's kind of easy to demonstrate. So that's what we want to do right now. And then it's sometimes a little bit clumsy to try to do it by hand, but we'll practice that also. When we get the chance. Not sure if we'll get to that today or not. So what I have drawn here is just that this is just some hypothetical function named f. So I just made it so that you know, it has kind of a nice curve here. So there's f, and I don't have a formula written down for it, but I do have some points there plotted on the graph of f. Now, you can sort of tell from the graph that f is going to have an inverse, right? Because this function f is always increasing, right? Well, if it continues in this same pattern that we're seeing here, at least, it's always increasing, right? From left to right. And so that means that it's not going to repeat a y value, because the y values are always going up from left to right. So none of the y values would be repeated. So so f will have an inverse, okay? And because I've got a couple, some points here plotted on the graph of f, we can sort of get an idea of what the graph of f inverse will look like. So let's look at these points: minus 6, 0, minus 2, 3, 2, 4, 4, 6, right? Those from the way I drew the graph of f, I know those points are on the graph of f. So that means on the graph of f inverse, you'll have the inverted points, right? So on the graph of f inverse, since 4, 6 is on the graph of f, on the graph of f inverse, you'll have the 0.64, right? And since 2, 4 is on the graph of f, on the graph of f inverse, you'll have the 0.42, and so on and so forth. Did I miss one there? Let's see. I also have -2, 3 on the graph of f, so that means the 0.3 minus 2, right? Which is this point would be on the graph of f inverse. And then since -6, 0 is on the graph of f, that means the 0.0 minus 6 there is on the graph of f inverse. So notice when you plot those points there and then connect them with a smooth curve, right? You get a curve that looks like this. Now, at first glance, you might not make much of that, right? So there's what the graph of f inverse apparently looks like, right? But here's the relationship between those graphs. So if someone points it out to you, then it becomes easier to see. So what I'm going to do is I'm going to put in here a 45-degree line. That's this dashed line. So the equation for this line is y equals x. All right, that's just a 45-degree line. So the x and y coordinates on this line are all the same. And when you put that 45-degree line in there, then you do see a relationship between the graph of f and the graph of f inverse. What the relationship is look, the graph of f inverse appears to be the graph of f rotated around this 45-degree line. So if you take f, right, okay, and then just rotate around this 45-degree line, that appears to give us the graph of f inverse, okay? So f inverse is really just a rotation of the graph of f, except not around the x or the y axis, but instead around this 45-degree line, okay? Now, actually, we're going to demonstrate that this is true, okay? So if you have a function f, and you want to know what the graph of its inverse looks like, that's really easy to discover. All you have to do is take the graph of f and rotate it around this 45-degree line, y equals x, all right? So we want to actually demonstrate that that's the case, all right? Not just for this function f, but for any function that has its inverse. Okay, now how in the world would how in the world can I demonstrate that? Okay, well, we're going to use tools that we already know, okay? Things that we've already learned about. So it's just some facts from geometry of rectangular coordinate systems that allow us to discover this relationship. All right, so let's imagine we just have any point a comma b that's on the graph of f, right? Okay, and of course that means on the graph of f inverse, what point will you have there? Of course, you'll get what? B comma a, right? So, but what I'm claiming is that if you take any point here, oh, my pen is really acting up. So if you take any point, a comma b, and you flip its coordinates to get b comma a, what I claim is you're in fact rotating that point around this 45-degree line. So you just get b comma a is just a mirror image of a comma b around this 45-degree line. All right, now how can we convince ourselves that this point is just a mirror image of this point through this or around this 45-degree line? All right, well, here's what I'm going to do. I'm going to connect AB and BA with a straight line. So let's draw that in there. Now, to convince you that these 2 points are mirror images of each other, right, around this 45-degree line, how can I convince you of that? Well, I think one thing that you would definitely say has to be the case, right, is this distance and this distance would have to be the same, right? Okay, because for this to be a mirror image right, around this line, these two distances, right, would have to be equal. Is that fair? Okay. All right, now, how can I convince myself, though, that these two distances really are the same? So the distance from this point to the 45-degree line and the distance from this point to the 45-degree line are really the same. Right now? Yes, yeah. So what are you suggesting about the midpoint formula? The same distance, right? The midpoint would have to be what? Would have to fall on this 45-degree line. I think that's what you're saying. Am I putting words in your mouth there? Right, okay. Yeah, sure, right. The midpoint between these 2 points would have to fall on this 45-degree line, right? Okay. If it does, then I think these distances have to be the same, correct? Well, we can calculate the midpoint though, right? Okay. So, because we know how to do that. So let's do that. Let's figure out what that midpoint is. And so do y'all remember how to do the midpoint? Yeah. The average of the coordinates, right? So let's average these coordinates. Let's average the two x coordinates. See, this x coordinate is A and this x coordinate is B. So when you average that, what do you get? You get A plus B, what? How do you average numbers? Divide by 2, right? You get A plus B divided by 2. And then for the second coordinate, well, this y coordinate is B, this y coordinate is A. Let's average those. So you get what? B plus A what? Divided by, are these the same? Yeah, that's really the same number, right? Okay. I just reversed the order of the terms of the numerator, but these are really the same number. But if you have a point and the x coordinate and the y coordinate are the same, guess where that point is going to fall? It's going to fall on this line, right? Okay. Because this 45-degree line is y equals x. That's the equation for this 45-degree line. It's y equals x. Okay. And if y equals x, that means the x coordinate and the y coordinate are the same. So this midpoint indeed, darn it. This midpoint indeed falls on that line, just like we hoped. Okay. So the distance from this point to the 45-degree line and the distance from this point to the 45-degree line are the same. Unfortunately, that's not quite enough to give us a mirror image. Okay. Because I can connect points on this curve and this curve where they have the same distance to this line, but they're not mirror images of one another. In fact, that's what kind of looks like happens in these 2 points, right? Correct? It looks like their distance to this 45-degree line is for both of these points is what? Is it 2? Yeah, I think it looks like it's 2, right? But those points are not mirror images of one another, right? See, around this 45-degree line. So I need something else to get a mirror image. Not just this distance has to be the same. It does have to be the same. But there's something else that's necessary to make this point a mirror image of this point. Can you see it you can see it in the picture here, right? When I draw this line connecting these 2 points and this y equals x line, how are those lines related to each other? So this line that connects AB and BA and the line y equals x, you can see it in the 2 dashed lines. How are those 2 dashed lines apparently related to each other? That doesn't happen here. Does have something to do with slope, but they're perpendicular, right? Okay. Oh, there it is, right? Okay. So this line that connects AB and BA has to be perpendicular to this line y equals x. See, this line that connects these 2 points, even though these 2 points are the same distance, right, to y equals x, they're not, these two lines are not perfect. So these are not perfect, they're integers. Now, so can we convince ourselves that these two lines that I've drawn here, this dashed line and this dashed line, can we convince ourselves that they're perpendicular? We know how to do this because what's the relationship between the slopes of perpendicular lines? Inverse, right? Inverse and something else. Opposite what? Sine, right? So you have reciprocal and opposite sign. All right, so let's check that. Okay. First, what's the slope of this line, though? That's so easy. So what's the slope of the line y equals x? 1, there it is, right? Okay. So it has slope 1. Now I just got to calculate the slope of this line. All right, what do I want it to turn out to be? Because I want these to be perpendicular. So what would I want that slope to be? -1, exactly. Let's see if this slope turns out to be -1. All right, so y'all know the slope formula. What do you do to calculate the slope between these 2 points? What's the slope formula? Yeah, y2 minus y1 over x2 minus x1, right? So take the difference in the y coordinates here. So let's do that. So let's take this y coordinate minus this y coordinate, right? What do you get there? This y coordinate minus this y coordinate would be what? This y coordinate minus this y coordinate, what? This one is a minus what? B. I don't know what a and b are, so I can't fill those numbers in, but it's a minus b divided by the difference in the x coordinates. What's the difference in the x coordinates? B minus a. A minus b over b minus a. What's that really equal to? That is really just -1. Okay. A minus b over b minus a, same as -1. Is that what I wanted? Well, the slope of y equal x is what? 1. Slope here is -1. So indeed, these two lines are perpendicular. And so there you're done, right? So when you take a point and you flip its coordinates, what you're really doing is just reflecting that point around what? What line? The 45-degree line y equals x. Okay. You're just rotating it around y equals x. So do that same thing for every point on F, rotate them all around y equals x. That would give you the graph of F inverse. Let's see if we can graph one then really quickly here. So f of x equals square root of x minus 2. I claim that function has an inverse. We'll make its graph and we'll convince ourselves of that. And then let's quickly sketch what the graph of f inverse looks like. We're not going to try to write down its formula. Let's just write its graph. So let's make the graph of f first. We'll do that just by filling in some values for x. So when x is 2, let's see, what do you get for y? This is square root, right? So what's the square root of 2 minus 2? 0, right? When you fill in 3 for x, you get square root of 3 minus 2, which of course is what? Which is 1, right? 4 is a little bit harder. When you fill that in, you get square root of 4 minus 2, which is the square root of 2. That's not a whole number, but we can approximate that. That's about 1.4. Okay. 6 is easier. When you put 6 in, you get square root of 6 minus 2, which is what? 2. So there's 4 points. We can make a graph with those 4 points. So let's see. When x is 2, y is 0, right? When x is 3, y is 1 up here. When x is 4, y is 1.4, maybe about right there. And when x is 6, there's that 1, 2, 3, 4, 5, 6. Y is 2, about right there. Let's connect those with a nice curve. So it's like this. That curve is always increasing. That curve is always increasing from left to right. So that function has an inverse, right? It's always going up. So that means you cannot repeat any y value. So indeed, the graph of f will have an inverse. Let's see if we can graph its inverse now really fast. So how do we graph the inverse? What's the trick that we pull? All right, well, sort of scribble in or visualize this 45-degree line, y equals x. And then what are you going to do with this curve? You're going to rotate it around y equals x. So you have to visualize that. You're going to take it and rotate it around this 45-degree line. Rotate it around 45-degree line. So when you take that curve and rotate it around this line, roughly what's that going to look like? So can y'all visualize that? Take that curve, rotate it here. What does that look like? You're going to look something like this, right? More or less. Just take that branch, rotate it around that 45-degree line, get something that looks like this. Okay, we're going to try this now a little bit. All right. So for you guys at home, see if I can find this activity. For you guys in class, I'm going to give you this picture. All right, these 4 graphs. So here are 4 functions. See, the first one looks like the sine curve, right? Okay. So well, that probably is the sine curve. So here's my question for each of these are all functions. For each of these functions, does it have an inverse? In other words, is it 1-to-1? Yes or no? And if it does have an inverse, then see if you can sketch inverse, okay? So try sketching inverse. If it's not 1-to-1, of course, don't try to sketch the inverse, right? Okay, so you just mark that one as no and go on, okay? But if you think it is 1-to-1, does have it, and that's, I think, draw in that 45 line, see if you can figure out how to rotate that curve around the 45 degrees. Okay. Not always trivial task. Okay. So first look through them quickly and decide if they have inverses or not, because there's no use in working on something that doesn't have it. Right. So let's do that first. Let's decide if there you go. Let's decide if it has an inverse. So let's quickly decide if it has an inverse or not. What do y'all think about 1? Does that have an inverse? No, definitely not, right? Because there are lots of repeated y values here. In fact, if you look along the x-axis, this has lots of x-intercepts, right? So there's going to be a lot of points where y equals 0. So definitely not an inverse. So sine function does not have an inverse. That's kind of a disappointment. Sine curve, no inverse. What about 2? I think so, because that is always increasing from left to right. That means you cannot have repeated y values if it's always increasing. What about 3? Yes, because that one's always decreasing from left to right. So you're not going to have repeated y values. What about 4? No, that's like the sine curve, right? Lots of points there will have repeated y values. For instance, if you look at y equals 2, right? There's 3 points that have y equal 2 there as their second coordinate. So no, so you're just looking at 2 and 3. See if you can sketch the inverse there. So drawing the 45-degree line and try to think about rotating it around the 45-degree line. 3 is really the trickiest one, I think. I'm not sure I know what that one looks like.
Oh, I see. Okay. Gotcha.
So. Oh, yeah. All right, then. Yeah, nothing. That's it. That one's hard. Yeah, so what did I realize always? So this one. So. Hard.
Because you were flipping it over this.
This one's harder. Yeah. That's a nice reference. Think about this. Nope. I'm inverse. Yeah, don't try that. Okay. Draw out the 45. Section. So think about this section. Go to. And draw that little piece there. Rotate. Yes. So do it for the other two pieces. Same idea. Yeah. But what is it? However, that doesn't even look like a. Yeah. I think one piece is lost. Attention. Those first are counts. That right here. Oh, no. Back of my room. And then you get number.
It is like,
Hard.
look, close. So it's like, so cross. He made me think, a little bit over.
Yeah.
So, what I did, what I like to yeah, there's nothing on the line. And right now,
Yeah, that's what I'm saying. Yeah. Okay. It's like it says.
Okay, let's, did y'all have any luck there online? Online people, it's kind of hard because you don't have the graph on paper there to work from, so you have to sort of duplicate it. Well, let's draw it here. And but at least this one, we may have to finish this one next time. Okay. Let's try 2. That one's the easy one to see what the inverse looks like. But you really need to put in first the 45-degree line. That really helps as a reference. So there's the 45-degree line. Remember, in the 45-degree line, the X and Y coordinates are the same. So draw 2, 2, 4, 4, 6, 6, right? Okay. And then likewise on the left-hand side there. Okay. So draw that in first because you're going to think about rotating this curve or reflecting this curve, if you want to think of it as a mirror reflection. For some people, that's easier, around this 45-degree line. But I would take it in pieces because that the little pieces are easier to work with than the whole thing at once. So maybe start with this middle piece, right? This middle piece right here, the piece that's above the 45-degree line, and think about if I reflect that around the 45-degree line or rotate it around the 45-degree line, what am I going to end up with? You're going to end up with something like this. Does that make sense? Okay, because again, think of the rotating this curve around the line. What about this piece if you rotate it? Well, you're rotating it above, correct? So you're going to get something like this, right? Same shape, but rotated. And then what about this piece is a little bit harder to understand. If that rotates around the 45-degree line, what happens? You end up with a branch like this, maybe? Is that right? Take this and rotate it up. So, well, it's kind of hard to tell which curve is which right now. Okay. But there's the graph of okay. Same thing for number 3. Draw in first your 45-degree line and then try to visualize rotating the pieces. Be easier if you had lots of places where this curve intersects the 45-degree line like we have here. That makes it easier to see the rotation, but this is tougher. All right, so think about this at home, right? If you didn't get it, if I rotate, say, this branch around this 45-degree curve, what's that going to look like? Or if I rotate this branch around this 45-degree curve, what's that going to look like? Okay, when if you do both branches correctly, keep in mind you'll get the same shaped curve ultimately, right? Just rotated. Okay, so you'll have a curve shaped like this, right? Shaped like that, but it's going to be oriented differently, right? Because you rotated around that 45-degree line. Okay, well, we'll finish that one then. We'll try finishing that one next time. Okay, for those who have a sheet, y'all can play with it also. If it comes down to it, if it gets down to it, try picking coordinates off of this curve and flipping the coordinates, right? Okay, and then connecting them. Normally we try to avoid that, okay, we just want to try to visualize what the inverse looks like, but if you get desperate, try actually guessing what coordinates are on this curve, flipping the coordinates and plotting those to give you a better idea of what the inverse looks like. Okay. All right. So, well, we're done for today. And we're about through talking about, well, we're through talking about inverses pretty much. Okay. Finally, we're going to get to apply all this knowledge to sine and cosine and tangent and so forth curves. All right. We're going to revisit those curves, those graphs next time. Okay. So I'll see you all guys on Monday. You've got a homework assignment due Thursday tomorrow, but not another one until Monday. That's on composition and inverses.